Good morning. Today's topic is introduction to compiler. Right. So before we enter into the topic, we must know some basics. So that I have to include the basics: computer languages, language processing system, for understanding the compiler. Right. So these are our outline: computer languages, language processing system, then compiler. In compiler, I am going to discuss the role of compiler, types of compiler, parts of compiler, and various phases of compiler, along with a case study. Computer languages. So we know what is language. Language is a communication tool, right? English is a language that is used to communicate between man to man. Similarly, computer languages, we have thousands of language for communicate with the computer. The computer languages are classified in various ways. One of the ways, based on the level of language, it can be classified into three levels: low level, middle level, and high level. The low level language, the first computer languages comes under low level. The first computer language is machine language. Machine language. The character set of the machine language is zeros and ones. It means we can write the program only with the use of zeros and ones. Whatever you do with this language, you must use zeros and ones. For writing your program, for giving your data, everything should be in the form of zeros and ones. That is machine language. So that it is very, very difficult to write the program. It is very difficult to understand. Modifying the code is very difficult, but no other way. Our computer only knows zeros and ones, that is high and low state. So no other way we must write our program using zeros and ones. But it does not need any translator, because our computer knows zeros and ones. So whatever you write with zeros and ones, that can be easily or directly understood by the computer. So that there was no need of translator. So because of this reason, the execution of machine code is very, very fast. But the main drawback with machine languages, these languages are machine dependent language. It means if you write a program for one language, that could be executed with that machine, not with the other machine. So if you develop a software with one machine, that can be executed for the same set of architecture only. That is the main drawback. So that we intended to go to the next level of language, that is middle level language. The assembly language comes under this category. So instead of using zeros and ones, so here in assembly language they are going to use mnemonic codes. Mnemonic codes. For example, here it is move. Moving a data from A to register R1, add, addition of two register, sub, mul, div, jump, start, stop. So these are all some of the mnemonic codes. Using this we can easily write our program. By the way, anyone can easily understand the program. You can go for modification and other things. So that's why we comes to assembly language. But we know the computers only knows zeros and ones, so that we need a translator. That is, the mnemonic codes could not be understood by the computer, so that the mnemonic codes should be converted to zeros and ones. For that we need to use a translator called assembler. So assembler is a translator which translate the assembly language program into machine code. By the way, only you can execute your program, right? So because of this translation process, it may take some additional time, no other way. So the advantage is we can easily understand, but again the drawback is machine dependency. Assembly language also a machine dependent language. It means if you write a program for a particular machine, that can be executed with that machine only. So that we can go for the third level of language, high level language. So other than machine and assembly language, all other languages are comes under high level group, right? We know Fortran, Pascal, C, C++, Java, VB are all the languages comes under this category. So the character set of high level language is statements. See, in low level they are using zeros and ones. In assembly they go for mnemonic codes. Now you can write the statement C equal to A plus B. So this way you can write any statement, print, import, see anything as statement, so that it is very easy to write your program. Anyone can easily understand anybody's program, right? Again, we are writing our program using statements, so that it need a translator. The translator is compiler. So what is compiler? Compiler is a translator for translating a high level language program to other form of language, right? So the advantages: easy to write, easy to debug, test, everything is easy. And most importantly, the high level languages are machine independent language. It means if you write a program for a particular computer, that can be executed in any other computer. Recently we have Java. So Java is machine independent as well as platform independent. Means if you write a program for Windows operating system, that can be executed to Linux operating system also, right? So totally machine independent and platform independent. So that's why we are in the era of high level languages, right? So for translating the high level languages, we need compiler as translator. The language processing system. So we have thousands of languages, right? So how the languages are processed in the computer, right? So source program, otherwise called the user program or skeletal program, that is written by the user, that is given to preprocessor, a system software, right? Why it is called preprocessor? If you do anything before compilation, that is called pre-processing, that is done by preprocessor, right? A preprocessor which modify the source program into input for the compiler, right? There are some tasks. First one is macro processing. Macro processing. See, if suppose you have a C language, pi is a symbol, you can define pi is 3.14, called macro. So hereafter with your program you can use pi. Wherever you have pi, that is replaced with 3.14, that is done by the macro processing. Second one is file inclusion. So nowadays all the languages have much more library functions. All the library functions are stored in some library files. Before using the library function, you must include all the header file. For that we have to use the file inclusion process, that is done by the preprocessor. Then rational preprocessor. It is possible to embed some other language with C language. For example, it is possible to execute assembly program within C program. Similarly, it is possible to include some SQL query into C language with the help of the rational preprocessing. The last one, language extension. See, whereas in the older language there are some statements not available, it is possible to include such statement with your language with the help of language extension. Anyway, these are the things, tasks done by the preprocessor, anything done before compilation, right? How the compiler, right? The modified source program is given to the compiler. Yes, the compiler is a translator, right, which translate a high level language program into other type of language. It may be assembly language or it may be a machine language. Anyway, compiler is a translator, translate a source program into another form of the code. Then assembler. Assembler also a translator which translate the assembly language program into the machine code, right? Now the machine code, The next level is loader and linker. So we are using so many library functions. All the functions are already compiled and the object codes are already available. That code should be linked to your program. By the way, only you can use your library function. Further, you have to use linker. So linker, another system software which link all the library files to your file. By the way, collectively it considered as a single unit, right? Then after the linking process, the total single unit should be loaded to the main memory, because all the programs can be executed only from the main memory. That is done by the loader. So then only we can go for the execution. So totally, so these are the process, a common process for executing any computing language programs. Source program modified by preprocessor, compiler translated to assembly, then assembly translated to machine code, then the libraries are linked and finally loaded for execution. Now the topic compiler. So already discussed, compiler is a translator which translates a source program, a high level language program, into another form of a program. That may be an assembly program or it may be a machine language program, right? Source programs, nowadays we have thousands of computer languages. For each language there is a separate compiler. For example, for C there is a separate compiler, C++ another compiler, for Java a separate one. So similarly, for all computing languages we have a special compiler, right? Even for C, TC Turbo compiler, MC Microsoft compiler, Borland compiler, IBM compiler. So by the way, there are so many compilers for separate languages. So thousands of computer languages consider as source language that is given to the input for the compiler. The target program. So the compiler compile the program and it may give a output as assembly code or a relocatable machine code or absolute machine code. The absolute machine code can be directly executed in the computer. So the compiler can produce any one of this target code. Yes, error handling. So compiler not only translate the program into target code, also it handle the errors. If suppose I compile one program, if there is any error, that errors are immediately reported to the user. By the way, only the user can correct the error and they may go for the execution. So error handling, and also it may go for some error correction. The compiler automatically go for some error correction also. Then optimization, the most important task of the compiler, right? The user writes some program, the compiler does not generate a target code as such. It may go for some optimization, that is, it going to reduce the code, or it going to make an efficient target code by the optimization process. So a compiler is a translator, accept the source program as input, right? Checking for the errors, report the errors or correct the errors. If our program is error free, it may go for the target code. Our target code may be any one of the type. Additionally, it may go for optimization. Based on the functionality of the compiler, we have some types. The single pass compiler, it means the compiler going to read the source program only once. By reading the program only once, it may go for the compilation process. Single pass compiler. Then multi-pass compiler, some compiler must go for more than one scan. That is, first time it going to scan our program. For some necessary, it may go for a second scan or third scan or any number of scan. That type of compiler is called multi-pass compiler. Third one, load and go compiler. or load link compiler. So this compiler going for compilation, after the compilation it may go for the execution, like interpreter. Interpreter is another translator that go for translation as well as for execution. Similarly, the load and go compiler compile the source program, load the program, and it may go for the execution. The debugging compiler, some compiler allow debugging operation also. By the way, the user can go for the error finding. And finally, optimizing compiler. So nowadays we have optimizing compiler. The compiler automatically go for some optimization. So anyway, based on the functionality of compiler, it may go for these types. Now the phases of compiler. The compilation process, it may done using several steps or several phases. Normally it took 6 phases. Some compiler they may go for 7 phases or some other things. Anyway, most commonly the compilers have 6 different phases. Start from lexical analysis, syntax analysis, semantic analysis, intermediate code generation, machine independent optimization, and finally code generation. For all the 6 phases we need some supporting functions that called a symbol table as well as error handling mechanism. So the symbol table which is connected to all the phases, similarly the error handling also connected to all the different phases. So totally here we have 6 different phases, whereas the recent compiler may have one more stage called optimization after the code generation. That is, machine dependent optimizations are done only after the code generation. So by the way, we can get the 7th phase also. Right. Now parts of compiler. Right. So we have 2 parts: analysis part and synthesis part. Analysis and synthesis. Right. So the first 4 phases, that is lexical analysis, syntax analysis, semantic analysis, and intermediate code generation, comes under analysis part. See, the compiler going to analyze the source program and create an intermediate code. Right. So that is done in the analysis part, which is most depends on the source language. The second part, synthesis part. So here the synthesis part will accept intermediate code as input and go for a target code, which is fully depends on the machine. Right. The analysis part based on source language, the synthesis part based on the machine. Right. Grouping of phases. So here we have 6 different phases that can be grouped into 2, front end and back end. So in the front end going to group the first 4 phases, the rest of the phases may be considered as back end. So front end, which is language dependent, the back end depends on the machine, The purpose of grouping the phases is we can go for reduce number of scanning. See, normally for each phase, for example lexical analysis, we need to read the program top to bottom. Then for syntax analysis, again you must go for the scanning. So this way for each phase you must scan the program from top to bottom. Instead, we are going to group the phases into one, and here the first 4 phases are grouped. By the way, within a single scan it is possible to do all the 4 phases. Right. So the purpose of grouping the phases is reduce number of scanning. By reduce the number of scanning, it is possible to reduce the total compilation time. Right. But it requires more memory. Right. Because for all the 4 phases we are going to read our program only once. Right. The intermediate results of each phases should be recorded in memory. By the way, only we can avoid the number of scan. So the grouping of phases may require some more memory. Right. So now I am going to explain the each phases of compiler detail. The first one is lexical analysis. called lexical analyzer, right, otherwise called scanner or linear analysis. So the lexical analyzer going to read our source program from top to bottom, left to right. The role of lexical analyzer is form the token. Okay, for finding the token, it must read the program top to bottom and left to right. At the time of reading the token, it going to skip all the blank spaces. So the lexical analyzer going to form the token and skip the unnecessary spaces. Also the lexical space handling the lexical errors. So what are lexical errors? If the lexical analyzer could not form a valid token, that means there is a lexical error. Okay, so here we have a diagram, the source program, right? The parts of the source program is called lexeme, right? It's nothing but the character stream. The character streams are called lexemes, that is given to lexical analyzer using the regular expression and finite automata. It's nothing but some of the rules. So using the rule, the lexical analyzer going to check whether the lexeme is valid token or not. If it is a valid token, the token may be given to the next phase. Otherwise, it may report the error. That is, if the lexeme does not match with any one of the regular expression, that means it's an invalid lexeme. So invalid token. So immediately the lexical analyzer report the error. Okay. For example, there is a high level language statement, position equal to initial plus rate into 60. A high level language statement. Now the lexical analyzer going to read this statement top to bottom and left to right. Here we have only one statement, so it's going to read it from left, position. It's going to read from left to right, right? P a character, O another character. So the lexical analyzer read the character, right, until it get a space or any other symbol. So by the way, it's going to read a character stream, position. After reading the character stream called lexeme, it's going to match with any one of the pattern. What is pattern? A rule that is specified by the regular expression or by the finite automata. For example, here position is an identifier token. And what is the rule for an identifier? A identifier, a letter followed by a letter or a number. So this is the rule for any valid identifier. So here the lexeme is position, start with P followed by some alphabet, so that a valid identifier token. So this way the lexical analyzer going to read the lexeme, right, and try to match with any one of the pattern and try to identify a valid token. If not, it report the error. The error is called lexical error. So here position, initial, rate, all the three are identifier token, equal assignment symbol, plus symbol, and 60 is a number also a token, right? So what are the token here? Identifier token, some symbols and number. Additionally we have keyword. For example, in C language, main is a keyword. The pattern for this keyword is the word main. Okay, so by the way, the lexical analyzer going to identify valid token, right, from the character stream. These tokens are given to the next phase, that is syntax analyzer. Okay, in the second phase of the compiler, syntax analyzer, otherwise called hierarchical analyzer or parser. Okay, so now the tokens, the separated by the lexical analyzer, given to syntax analyzer. So look at this, the source program given to lexical analyzer. The lexical analyzer find the tokens, right? The tokens are given to syntax analyzer. So the input for the syntax analyzer is the token and context free grammar. See, for any language there should be some grammar, you know. For English there are some grammar, we must follow the grammar, right? Similarly for computer languages also we have some grammar, that is there should be some syntax, you know. For C language all the statement must end with semicolon, there should be a main function, open braces then close braces. So these are some grammar, so that are given by the context free grammar. Okay, now the syntax analyzer get the token from lexical analyzer, then group all the tokens, right? The group of token must follow the rules prescribed by the context free grammar, otherwise the syntax analyzer report syntax error. For example, C equal to A plus B is our statement. As per C language, all the statement must end with a semicolon. That is the rule that is given by your context free grammar. If suppose you are not apply your semicolon in C language, that may raise one error, statement missing. That is, that error is reported by the syntax analyzer, because the statement C equal to A plus B without semicolon does not match with the context free grammar. So the role of syntax analyzer is it going to group all the token into meaningful braces, right, and check whether it is follow the rules prescribed by the context free grammar, then only it accept the syntax and generate a syntax tree. So the input for the syntax analyzer is tokens, the output of the syntax analyzer is syntax tree. For example, take the same case, position equal to initial plus rate into 60, right? So these are all separated as token by the lexical analyzer. Now the syntax analyzer going to check whether it follow the syntax, then it may go and draw the syntax tree. Look at this. So the syntax tree is constructed based on the context free grammar rules, right? So here multiplication is higher precedence than plus. So at the leaf we have the higher precedent computation, then the lower, so on. So right, anyway the tokens are now constructed as a syntax tree by syntax analyzer. Then the third phase, semantic analysis. Semantic analysis, generally can call the semantic analysis is the heart of the compilation process. It's going to do so many things, right? It check for semantic error and for some type information, right? Type information. Static semantic checks. So this phase going to check some static check. It's nothing but the check during the compilation time by the compiler. Static semantic checks are performed at compilation time. So what are the checks? It's going to check for the type. For example, C equal to A plus B, a statement. A, B, C all should be in same type. Then only the semantic analyzer may clear the statement. Otherwise, it may report an error, that is type mismatch error. So that it go for type checking. Then every variable is declared before it used, right? You know the C language rules, all the variable must be declared at the top. that is before the usage of any variable. That is checked by the semantic analyzer. If suppose you are not declare any variable, straight away you go for using that variable, then the semantic analyzer may give the error message, undefined variable. Okay. Then identifiers are used in appropriate context. See, for example, A equal to B, a valid statement. A equal to B, right? A equal to 10, a valid statement. 10 equal to A, is it valid? No. So by the way, the variable should be used in appropriate places. Then check for subroutine call arguments. You are going to call one subroutine, that is you are going to call one function. For example, add, the function going to add two variables, right? You are going to pass 3 arguments. Actually you are return the function for 2 arguments, but you are going to pass 3 arguments. Is it possible? No, because your function can accept only 2 arguments. So that is checked by the semantic analyzer. And check for labels. Suppose you are going to call, that is your apply a statement, go to XX. Here XX is the label that should be placed in any one of the place in your program. So these things are checked by the semantic analyzer during the compilation time. So that's why it's called a static semantic check. Whatever you did in compilation time, that is called static semantic check. Also dynamic semantic check. Dynamic, whatever you do in runtime, that are all considered as dynamic check. Dynamic check, what are all you do with runtime, that are all considered as dynamic checks, right? So the compiler produce some code, that code going to check during runtime. Anyway, it is under the control of compilation, right? The checks are array subscript values are within the bounds. Suppose you are declaring one variable integer a of 10, right? During runtime you try to give more than 10 values, right? See, our array is declared for the size of 10, but you try to give more than 10. So that type of errors are checked by the dynamic semantic check. Similarly, arithmetic errors, divide by 0 error, right? Suppose there is a statement C equal to A by B, right? If suppose you are giving the values A 10, B 5, the result may be 2. If suppose your inputs are A 10, B 0, now the computer could not divide anything by 0, the error is called divide by 0 error. That's also checked by the semantic analyzer during runtime. Similarly, pointers, okay. Before assigning any pointer, dereference, the value should be initialized to the pointer. So these type of runtime errors also checked by the semantic analysis. So the semantic analyzer mainly check for semantic error as well as for type errors. Here our statement is position equal to initial plus rate into 60. You know, 60 is an integer, rate is a real value, right? Before do any arithmetic operation, both operands should be in same type, whereas here there is a type mismatch. 60 is an integer, rate is a real. So the 60 should be converted to real, then only we can go for the multiplication operation, right? That is done by semantic analysis. So it go for type checking and also it go for type conversion. If possible, the compilers are go for type conversion. By the way, the integer value 60 is converted to real into real, then it may go for the operations. Okay. Anyway, for semantic analyzer, the input is syntax tree, the output also a syntax tree after type conversion. Right. So here we have 6 phases. There are 2 boxes, that is symbol table manager as well as error handler. Both are common for all the phases, right? So here symbol table. What is symbol table? Is a data structure. Symbol table is a data structure which is going to maintain all the symbols along with the attributes. For example, if suppose you are declare one statement integer a, okay, so here a is the symbol that is immediately recorded in the symbol table. Symbol is a, the type of the symbol is int, size of the symbol is 2, the address for the symbol, the scope of the symbol. So this way there are so many attributes for each symbol, all are recorded in the symbol table. Okay, you know our lexical analyzer read the tokens, that is it read the symbol. The symbols are immediately recorded into the symbol table. Then the syntax analyzer, right, it going to create a syntax tree. For that it need the tokens. For that it going to refer the symbol table, right? The semantic analyzer, you know, it go for the type checking. All the type informations are available in the symbol table, so that the semantic analyzer also go and refer the symbol table for the type of the variable. So this way all the phases are connected to symbol table. Some phases update the symbol table, the other phases may use the symbol table. Anyway, all are connected to symbol table. Similarly, another common phase is our error handler. So here we have 6 different phases. For each phase there are some error, lexical error. Okay, see, look at this types of errors: lexical error, syntax error, semantic error, logical error. So these are the common types of errors. Okay, anyway, all the phases are connected to some errors or some error handling mechanisms, right? Lexical errors. What are lexical errors? The role of lexical analyzer is it form a valid token, read the character and form the token. If the lexical analyzer could not form a token, means there is an error. That error is called lexical error. Okay. Syntax error. See, all your statements should follow the rule specified by the context-free grammar. Okay, if it violates, then there is a syntax error. For example, missing of semicolon. In C language, the statement should end with a semicolon rule. If you are not giving the semicolon, that is considered as a syntax error. Similarly, A equal to B, a valid assignment statement. Suppose your statement is A, it is not a valid statement. A plus plus, it may be a valid statement, but A itself, it's not a valid statement. So that type of errors comes under syntax error. Then semantic error, we discussed in earlier, all the type mismatch error. For example, A is integer, F is float, F equal to A, it is not possible. It is not possible to assign an integer to float. Similarly, A is an array, B is a normal integer, it is not possible to assign B to A directly, right? Similarly, all the variables should be declared before the usage. If not, it comes under semantic error, right? And finally, logical error. Okay, some logical errors also detected by the compiler, right? Because logic is only created by the user. The user can write their own program, right? But the compiler can identify some logical error. For example, code not reachable. Code not reachable. You are writing one if statement. If the condition 1, it means the condition is always true. If you are write anything in the else part, it never be reached, because our condition is always true, so that our control flow never reach our else part. That codes are called unreachable code that may be eliminated by our compiler. Similarly, infinitive loop. You are writing one for statement, right? You never increment your index value, so your loop may never end. So these type of errors are called logical error. Anyway, all these errors are detected by the various phases of compiler. Either it correct the errors or it may report the errors. Okay, so here we have some error correcting mechanism, right? All the phases detect the errors as well as it go for some correction. Panic mode error recovery scheme. Panic mode error recovery, generally used by the lexical analyzer. The lexical analyzer read the character, try to form a character token. If suppose there are some extra characters, for example, your statement is if. Instead of using the keyword if, right, you are wrongly pressed one more f. That is, you are pressing as if. It is not comes under the keyword token, because the keyword for if statement is only if. Here you have one more f that may be removed by this mechanism, panic mode. It delete the extra character until it get a valid token. That is panic mode error recovery. It going to delete the extra character until it get a valid token. Similarly, the statement mode error recovery schemes, right? Suppose you are missing to apply the semicolon, right? The compiler know there should be a semicolon here, then it may go for applying the semicolon. Similarly, if is the correct keyword, instead you are typing as fi. For typing if, you go for fi. So the compiler know the user tried to type a if statement, but they wrongly typed as fi, so that it may go for the interchange of the character. By the way, it can get if. So this way it may go for some insertion of new character, replacing of character, or deleting of character. By the way, it try to get a valid token. Then error protection. The compiler may know some common errors. For example, the common error is C language, all the statements should end with a semicolon. But most of the user, most of the time they miss to apply the semicolon. So here we are going to add one more protection to our context free grammar. Okay, what is our actual grammar? All the statements should end with a semicolon. Instead, our compiler add one more grammar, that is one more rule, protection, as a statement without semicolon. So by the way, the compiler may accept a statement with semicolon as well as a statement without semicolon, called error protection. The global correction algorithm based mechanism. You are writing one program, there are some errors. The compiler looking your program, there are some error. It go and check some existing program which is closely matched to this program. Then immediately it exchange that program. The user write one program. Already the compiler have some program very similar to this program, right? Now it go for the exchanging of program. It may be very costly, but anyway there is a mechanism called global correction. Anyway, the compiler have the additional mechanism called error handler connected to all the phases, right? It may find the errors, try to handle the errors, or it may report the errors. Now the next phase, intermediate code generation, right? So here character stream converted to token, tokens are converted to syntax tree, syntax trees are converted to again syntax tree with the type conversion. Now that is given to intermediate code generation. So it is not possible to generate a target code directly from the source program, right? So that the source programs are converted to some other form, abstract machine, a code for abstract machine. Then this abstract code is maybe converted to the actual code. Okay. Anyway, the intermediate code get the input from semantic analyzer and generate an intermediate code. So the intermediate code may be in three forms: the postfix form, syntax tree, or a three address code. You know what is postfix form? A plus B is the statement. The postfix form is AB plus. And you know what is syntax tree? The syntactical structure of the statement. Or the three address code. The three address code is nothing but a code may contain maximum of 3 operands. That codes are called three address code. Okay. So here we have a three address code. As per our example, our statement is position equal to initial plus rate into 60. We have the equivalent intermediate code. Okay. See. Yes. First, it going to create a intermediate form for this conversion. The 60 is converted to real, then it may go for the multiplication, then it may go for the addition, then it may go for the assignment, right? See, into real conversion, multiplication, addition and assignment. So the intermediate code is generated likewise. First it going to convert 60 to real, then that is multiplied with a temporary, then that is added to another temporary, and finally assigned to the identifier. Okay. Then the code optimization. Okay, code optimization. It's already discussed. The main role of the compiler is translation, as well as it go for some optimization. That is, it going to reduce the code, or it going to eliminate our unnecessary code. So without violating the objective of the program, the compiler go for some modification, right? Because the user commonly made some mistakes, or they may use some redundant code, unnecessary code, unreachable codes, dead codes, all should be eliminated, right, by the compiler called optimization. There are two types of optimization: machine independent as well as dependent one. Machine independent in the sense the compiler go for some optimization without considering the machine instruction, whereas the second one it go for the optimization only based on the machine. Okay, some of the common optimization technique: redundant instruction elimination, right? For example, as a user I am writing this code A equal to B, then after some time again I am going to write the same code A equal to B. Okay, so the same statement repeated twice, so the compiler go and check it. Is there is any statement repeated, it may eliminate one. Redundant instruction elimination. Unreachable code: sometimes some part of our program never be executed. That codes are called unreachable code, that may be removed. Then algebraic simplification. For example, x equal to x plus 0, it does not change the value of x, right? So So you need not to go for this statement. Similarly, x equal to x into 1 does not change it. X equal to x by 1, unnecessary. So these code may be eliminated, as well as x equal to x square. Our statement is x equal to x square. That may be written as x equal to x into x. By the way, our target code may be efficient. The fourth one, strength reduction. Right? In optimization, the most important area is looping. Right? If you reduce only one instruction in the loop body, it may cost more. So that we need to apply our optimization in the loop. So here we have a technique called strength reduction. If possible, we can move a code from the loop body to the outer part. So by the way, we can reduce the number of instructions very highly. And finally, accessing machine instruction. See, there is a statement a equal to a plus 1. So for that we need to use an add instruction. Add a with 1. By the way, you can get a equal to a plus 1. But some machine may have their own instruction. Increment a, inc a. Both are equivalent. Right? Instead of go for 2 instruction, you go for a single instruction. So by the way, we can reduce the code. So these are the commonly used optimization techniques. Okay. Right. So here you have our intermediate code, a 4-line intermediate code that can be reduced to 2-line code. That is called optimization, right? So integer to real, one conversion, you can go for direct multiplication with a float. Temporary 1 equal to id 3 into 60. So by the way, the 2-line is reduced as 1 line. Then instead of go for another temporary, you can go for the addition and assign the value id directly. By the way, a 4-line intermediate code can be reduced to a 2-line intermediate code. So you are reducing 50% of code. In the final phase, the code generation. Okay, after the optimization process, now you have optimized intermediate code. Now you can go for code generation, target code generation. Right? As we discussed, our target code may be a assembly code or a absolute machine code or a relocatable machine code. Anyway, the intermediate code, optimized intermediate code is now converted to the target code using the phase generation, code generation. So the output of code generation is either a relocatable machine code or an assembly code. So the code generation, right, must consider all those things. What is our target language? Either it is an assembly or relocatable machine code or machine. It must be considered what is the target code. Then what is the type of intermediate code? So already we discussed, in the intermediate code may be a postfix notation, or it may be a syntax tree, or it may be a 3-address code. Okay, so based on the intermediate code, it may be go for the code generation, right? Then instruction selection, right? If suppose your machine has increment instruction, you must go for increment instruction. Otherwise, you may go for add instruction. Already we have an example, a equal to a plus 1, our statement, right? So for that, you may go for add instruction or increment instruction. Better you go for the increment instruction, instruction selection. Then ordering of instruction. If it is possible, you can go for the reordering of execution. There are 4 instructions, right? You can execute 1, 2, 3, 4. Sometimes you may go for 1, 3, 4, 2. If the instructions are independent, you may go for changing of order of execution. Sometimes the changing order may reduce number of register usage. also it reduce the code. Okay, so ordering of instruction, and finally register allocation, right? The number of register used should be less, because generally in RISC architecture there are so many types of architecture. One of the architecture is RISC, reduced instruction set computer. So there only 132 general purpose registers, right? So the compiler can use only the 132 register as the maximum, right? So register allocation is also a vital role. So while the code generator go for the code generation, must consider all those things. As per our example, the optimized intermediate code that may be converted to one assembly code. Okay, so what are the operations? First we need to move ID3 to a register. Look at this, move ID3 register 2. Okay, then multiply ID, that is register 2 with 60, multiplication, mul f, multiplication of floating point number, a mnemonic code. Similarly, you are going to move that value to register 1, that may be added to register 2, and finally the result may be moved to the destination ID. Okay, anyway, optimized code and equivalent assembly code, a target code. Okay, some compiler may use machine dependent optimization. So using machine dependent optimization, it may go for further optimization. Okay, anyway, now we have the target code. Okay, so here the total process is explained with a case study. Position equal to initial plus rate into 60 is our source language statement given to lexical analyzer. So the lexical analyzer going to read the input source statement from left to right. It try to find the tokens. Here the tokens are lexemes are position is the lexeme, equal to lexeme, initial lexeme, all are lexemes. Now the lexeme is matched with identifier token. So identifier 1, assignment, identifier 2, addition, identifier 3, multiplication, a number. So these are all token separated by the lexical analyzer. Now the tokens are given to syntax analyzer. Okay, syntax analyzer. So the syntax analyzer, using the context free grammar, it going to form a syntax tree. Look at this, statement converted to tokens. So these are all tokens. The token stream now constructed as a syntax tree based on the rule. The syntax tree are called parse tree given to semantic analyzer. So the semantic analyzer going to check for type mismatches. Here there is a type mismatch. 60 could not be multiplied with identifier 3. Why? Because identifier 3 is rate, a floating point value, could not be multiplied with integer value, so that it must go for type conversion. 60 converted to real, then it may go for the multiplication done by our semantic analyzer. Okay, then I go for code generator, intermediate code generator. Okay, 60 to real. Look at this, into to real. 60 is converted as real and assigned to a temporary register. Then that result is added to identifier 3. Okay, code this, 60 converted to real, assigned to temporary, then the temporary one multiplied with identifier 3 that is assigned to temporary 2, that may be added to the identifier 2 that is assigned to temporary 3. Now the final result available in temporary 3 that may be assigned for ID 1. Okay, so this syntax tree is converted to an intermediate representation. Now that is given to a code optimizer. So the code optimizer going to reduce the number of code, as already discussed. This one is unnecessary because our machine may support a floating point multiplication directly, so that you can go for the multiplication directly. By the way, temp 1 equal to ID 3 into 60. Okay. Whereas in the earlier case you have to use 3 temporaries, temp 1, 2, 3. But here you are going to use only one temporary. That is the efficient use of temporary register, right? So ID 3 is multiplied with 60 and assigned to temporary 1. That may be added to identifier 2 and assigned to identifier 1. Anyway, a 4-line code is now reduced to 2-line code by the code optimizer. Okay, that is given to the code generator. For each intermediate code, okay, for each intermediate code, a equivalent target code is generated by the code generator. Okay, the code generator use some template, because if it is find one multiplication operation, it go and call a template for multiplication operation. For plus, it may go for the template. By the way, using the template, it easily and fastly generate the target code, right? As per our example, all are floating point operations, so that our instructions are comes with F, move, float, add, float, like that. Okay. So here you have the equivalent target code conversion, right? Okay, thank you.